Bless you. Let's start with this. How many ways can two lines intersect? All right. If you start thinking about how many different ways can two lines intersect, you guys just said once. Two lines can intersect once. They intersect at one spot. They can intersect infinitely. How do they intersect infinitely? No. Same line, right. Two lines can intersect. If they're the same line, they can intersect infinitely, like that. That's smooth. Oops. And then there's one other way. Zero. They could not intersect. How do they not intersect? If they're parallel. Okay. So there's three ways that lines can intersect, or not. You can not intersect at all, because your lines are parallel. If you're parallel, you have what in common? Slope. Okay. Infinitely, that happens when you are the same line. And then once, where you crisscross or cross at a specific point. Okay. Now, what that was getting towards, where I wanted to show that, is because when we start talking about systems of equations, we're solving for the intersection of two equations. We're looking for that. You can do that graphically. You can do that algebraically. Personally, I think graphically is fine, but it's a waste of time, especially when you're just dealing with what you're looking for. That. When you get into shaded systems, it's a little bit less you. It's a little bit more important to do things graphically. So when we go back to this, if I want to solve a system of equations using algebra, we'll do these separately. Using algebra, there's a couple of methods that you guys probably remember-ish. What was one way that you kind of remember-ish? Yep. You could subtract. You had, let's see, let me write this out. There was substitution. And then the other one was linear combination. You can add, or you can subtract. Just kind of reminding you, and it's the idea of which one is going to be better for specific situations. When do you use substitution? Nope. There are times you don't want to use substitution. Now, personally, I would use substitution only when I have a variable that has a coefficient of 1, or it's a variable that's already solved by itself, like it says x equals something, or y equals something. Then I would use direct substitution. I would use my linear combinations to make get a variable or to get coefficients that are the same by multiplying by factors. I would use addition or subtraction if I have the same coefficient, same signs, or same coefficient with opposite signs. And as we get into this stuff, you'll start to remember, oh yeah, I vaguely remember that from a couple years ago. So first thing I'm going to say is I'm going to use substitution for this one. Reason being, x has a coefficient of 1, and I can get x by itself rather quickly. All I have to do is move into y. So I can say that x is negative 2y plus 2. So what happens is I'm going to solve for one of the variables independently of the other. All right. So via direct substitution, I'm going to take this value of x and substitute into the other equation. Bless you. So we get 3 negative 2y plus 2 plus 4y equals negative 4. Now, here's a thing that most people screw up. Distributive property. When you distribute, you have to go to how many parts? Well, all of them are just the ones in the parentheses. Ones in the parentheses. Okay. If you sometimes people actually send that 3 to the 4. Why? Don't do that. Okay. So this may be silly, but take a second and draw the arrows. It'll force you to remember to go to 2 parts inside the parentheses. Okay. Excuse me. So you get negative 6y plus 6. And now you're at a 2-step equation. Okay. Moving some stuff around. Looks like I got negative 2y equals negative 10. Therefore, y is 5. Okay with that? What's that? What do you do now to figure out what x is? Substitute. Just substitute back up here. So 2 times, or negative 2 times 5 is negative 10. Negative 10 and 2 is negative 8. So write that out. Now the last thing here is, remember, you're dealing with the intersection of 2 lines. Those 2 lines intersected at a point. Points are called ordered pairs, so your answer will be written as an ordered pair. And that would be the solution. Right. Vaguely ring a bell? It's been a while probably since you saw that. Allergies. My eyes have been burning this week. Just no matter what. Right? Let's try another one. So here we've got x minus 5y is 11, and 2x plus 7y is negative 3. Once again, this is setting you up to do method substitution. So using substitution, what are you going to get by itself? The x. Okay. Therefore, x is going to equal what? Okay. X equals 5y plus 11, or 11 plus 5y, it doesn't matter. Either way, it works out just fine. That gives you the value to substitute into the other equation. Therefore, you're only solving for one variable at a time. Distribute through. So far, so good? Okay. Combine like terms. Subtract the 22 over, we get negative, what is that, 25? Okay. 5 by 17. Well, that's a crummy looking fraction. Now, is it okay that you get a crummy fraction? All right. Now, obviously, what happens here is that we have to substitute values back together. Well, can't we just substitute in without a big deal still? If I know what y is, excuse me, it's just going to be a really ugly looking fraction. Okay. Well, you remember how to make the fraction bar on your calculator? Alpha y equals? Right. What's that? No, and it's stretched out badly when it's not. It doesn't look right. So alpha y equals, gives me my fraction. What was it, negative, I forgot what, negative 25 over 17, right? Over 17. So we have to multiply that times 5. Gives me another fraction, plus 11. Gives me my fraction. Now, what's nice with these calculators, if you use the fraction bar, you'll get fractions back. Okay? You guys remember using the multi-do calculators last year, right? Same basic principle where if you use the fraction bar, it gave you fractions. It's the same thing. It's really, really nice. So don't worry, you're going to get crummy numbers. It happens. If you think that you're getting crummy numbers and you don't think you should be getting crummy numbers, just double check. This is the one section that more often than not, when you're doing problems out of the book, you'll read the start of one problem, you'll look down, write it down, you'll look back up, and you'll read part of another problem. This is the one section that it happens all the time. Okay? So don't freak if you get crummy fractions. It is entirely possible. If you are worried and concerned about that, by all means, remember, I keep the solution manuals. If you ever want to double check your work and whatnot, there is a worked out solution right here. By all means, anytime you want to look at it and see how you're doing, right here. And that's why I don't have such a huge emphasis on homework. Because everything is available to you guys to research and look at. I expect that you do it. I expect that you ask questions about it and go for it, but you know, if you're just going to make photocopies and copy it, it's not going to help you any. But I keep everything there for you. So, when we get 62 over 17, that was my y value, my x value. Oh, that was x, excuse me. Sorry. The other was negative 25. 17. And that would be my solution. Okay. It just looks crummy, but it works. With this, substitution is easy. Now what can you do? Exactly, right? Bless you. So I'm just going to skip right ahead to the goofier stuff. I heard you say it. Now, remember, there's a couple of things you can do when you're talking about systems. You can, if you have the same coefficient with the same sign, I would subtract them. Subtract one from the other to eliminate a variable. If you have same coefficient with opposite signs, I would add them together. This is for eliminating a variable. Okay? When you don't have the same coefficient, same sign, or opposite, or same coefficient, opposite sign, you want to create that. And that's what I mean by multiplying it by some scalar. Whether you're multiplying it by a whole number or you're multiplying it by a fractional amount, basically division, you can set it up in a couple of different ways. I would not try to solve this thing via substitution. I could say that x is going to equal 2y plus 13 over 2, and I could substitute it that way with fractions and all. It'll work. It's a pain. It is much easier to figure out some multiplier to get the same coefficients. And I heard someone in the back say, multiply the top one by 2. Okay. So what I'm going to do is multiply the top equation by 2, and I usually just rewrite it right underneath it. So in doing that, we get 4x minus 8y equals 26. Are we okay with that? Now, notice we have the same coefficient with the same sign, which means I'm going to subtract. Here's my little trick for you. When you're subtracting these problems, remember, you're actually subtracting 3 times. And I usually break it into those 3 sections, so that way I pay really close attention to my signs. It is so common that people will forget your signs when you're subtracting these things through. So 4 minus 4, fine, it's gone. Good. Negative 5 minus negative 8 is how much? It's 3y, yeah. 8 minus 26, that is negative 18. So it just splits it up into 3 problems so that way you know where everything's going. It's just a nice, easy way of keeping your problem, I don't want to say structured, but aligned, I think in order, something. Organized, that's the word I was looking for. Or, yeah, how organized I am. That gives me a y value of negative 6. And then, does it matter which one you go back to substitute in? Nope. So if I go back and just do 2x minus 4 times negative 6 is 13. 2x plus 24. Subtract over. Negative 11. So you're ordered here. All right. Not too bad, is it? You vaguely remember this? Good. That one. I want to do this one. All right, take a minute. Yes, sir. Yes, sir. Take a minute and go for it. Were any of you guys just glued to watching the hurricane hit everything? When my grandparents first retired back in the late 80s, early 90s, they bought a condo about 7 floors up, right on the beach, right in Marco, right on Marco Island, where that thing went right through. They were watching where where their high rise was. Their overlook would have just like right. You look down off their balcony, you're on the Gulf. It's so cool, but yeah, it's crazy. Anyways. So what do you do for this one? Right. So in this one, there's a couple of different things you can do. Multiply the top one by 5, the bottom one by 2. Did you do that? No. What did you do? Oh, all right. Now there's a couple ways you can go with this one. When you see opposite signs, I would always try to eliminate that variable. Reason being, a lot of times when you guys use subtraction with all the different sign changes, you're going to screw that up. No offense, but I know how you guys work. But when I see signs that are different, I know that if I can add them together, it'll be fine. Now, one of the things that you could have done here is also, notice that second equation, they're all multiples of 5. Now, what I could have done there is multiply that whole thing by 2/5. Reason doing that is that I would get rid of the 5 right away, and it would make everything a 2. So this would have been, if I did that, you guys are looking at me like I'm really Never even heard of it by a fraction. Fractions are okay, guys. It's all right. All right. So let's go the route you probably did. Multiply the top one by 5, the bottom one by 2. Okay. If you do that, you'll get right away, you'll see that you have, 10x, 15y, and a negative 5. Negative 10x, 10y, and a 30. Everybody okay with that? What I'm doing there is what we call linear combinations. You're multiplying tops and bottoms by some scales to be able to get the same coefficients. Whichever way you choose to go is perfectly fine. There is no one-size-fits-all for a lot of these. If you did note, if you wanted to do the scalar, divide everything by 5 and then multiply by 2, it wouldn't work. You would just have different values of coefficients. No big deal. Doing this, you eliminate your x value. So now these are gone. Add these together. Add these together. And what's y? And once you get the value of y, all we do is just go back up top and resubstitute it. I'll use this one this time. I get negative 5x plus 5 times 1 is 15. Bless you. Which gives me negative 5x is 10. X is negative 2. Okay. There is no one size fits all. Everyone probably can do one thing different here and there, and it's not a big deal. All right. Nick? What's that? I don't know. Yeah, some of these problems can get going. All right, give this one a shot. Here, if you take a GCF out, it just makes life quicker. Do you have to? No. But in my mind, I see that I can have a GCF up top. If I divide the whole thing by 4, I get x minus 4y is 1. Do the bottom one, I get negative x plus 4y is 1. Oh, excuse me, negative 1. Now, when I put those two together, what do you get? You get 0 equals 0, don't you? Now hold on here. If I add those all together, I get 0 equals 0. Is that a true or a false statement? True statement, which means what's your answer? Because that's the same line. That's the same line. That's the same line. That means it's infinite solutions. That means it's all real numbers. Okay? Forgot about that one, didn't you? Now, if you went the long way and multiply the top by 3 and the bottom by 4, you would have gotten there. You would have gotten through the same stuff. Okay? You would have seen the elimination would have worked. But as you simplify that stuff out, you have the same line. Okay? Does that make sense? Now, what happens if it went through and it said 0 equals 8? That's not true. And I would, even if you get 0 equals 0 or 0 equals 8, you get what would be called a false statement. Just go back and double check real quick. You might miss a sign. But it does happen. If it is a false statement, it just means they're parallel. No answer, no solution. Okay. But when you do get one, that's true, That's what that would look like. Tricky little ones. Tricky. No. 3x minus 8y is 1. 6x plus 2y is 11. Now in this case, you're trying to start there to think, oh, that's 6x plus 2y. Oh, then it's 11. Now here, does it matter which one you try to eliminate first, the x or the y? It doesn't. But if I were you, I would eliminate the y values. Why do you think I would say that? Exactly. If I try to eliminate the y values, I don't have to deal with negatives. I don't have to deal with subtraction stuff. Because if I start doing all that subtraction, then things go haywire. Right? So what I would do is I would just rewrite the top equation and multiply the bottom one by. So we have 24. Add these guys together. Bless you. What do we get? 27x is 45. Divide it out.
Smaller number.
Let's see, what is that, 5/3? You got 3/5? You done good. Now, even though it looks like it's going to be off because you've got a 5/3, if you substitute back in there, what's 5/3 times 3? It's 5. Okay. That's all right. You okay? You gave me you. Getting angry. Okay. And it's okay. So you just go back to the top. Then you have 3 times 5/3. You have 5/3 and 1/2. Is that what we got? 5/3 and 1/2. Okay. Remember, guys, there's a lot of different ways. It's totally dependent upon what you see in terms of how you want to set it up. There's really never like a one-size-fits-all. I mean, if you want to substitute all day long, go for it. It's going to take you forever. All right? Linear combination stuff, pick a variable to eliminate. Suggestion is always to try to eliminate the ones that have opposite signs because you're just adding. Because you start doing all that subtraction, the signs can get kind of screwed up. Also, when you're writing down problems, just make sure you write it down, carefully. It's so easy to write down parts of one problem and parts of another, especially in this. Okay. I did. I even left you a note saying I won't be at school on Tuesday. So it appears as though there's a lot. But if you think about it, you've got 2 days to do it. working today and tomorrow.